are glad to report our method and performance for ensembling target modeling in CASP16. So first, we can check our methodology parts. In CASP16, we actually have 5 groups partitioned in CASP this year. Sorry, which we have the Zheng server, Zheng modular, Zheng, and MI ensemble and NKRA server partitioned in CASP. And among of them, MI ensemble server and Zheng groups has some specific focus on ensemble targets modeling. But the Zheng group has the longer running. They are both based on the same methods, but the Zheng group has the longer running time and a more diverse set of the MSAs. This figure shows the overall pipeline used by Zheng group and MI ensemble servers. It contains 4 individual sub-pipeline for modeling protein monomer, RNA, and hybrid targets. So in this talk, we will major focus on the protein-related target modeling pipelines. This slide shows the modeling methods in ensemble fold for modeling protein monomers. This pipeline begins with the DeepMSA2 pipeline. It using 3 different sub-MSA construction tools to iteratively search the genome and metagenome database. Finally, we will get around 10 different kinds of MSAs, and those MSA will input to DMFold or AlphaFold2 structure module to get some structure decoys. And those decoys will be clustered by the structure similarity first, and the class center of each cluster, and the corresponding restraint, spatial restraint generated from the class center model, coupling with the knowledge-based potential from de-tensor force field, will be used guiding a replica exchange Monte Carlo simulation to get a more diverse set of the decoys. Finally, after the simulation step, we will use a program called MoClass to cluster those decoys to different clusters, and the class center of each class will be selected as the final model, and we will assign each model with each state. For the protein monomer ensemble target modeling, we use the DMFold monomer pipeline that we developed in the previous CASP. But this time we slightly changed the pipeline to improve the performance for modeling ensemble targets. First, in the MSA generation step, we actually enlarged our in-house metagenome database this year. Currently, it contains around 60 billion sequences in our database, which is almost the double size of the database we used in previous. In the MSA pairing step, we increase the number of the paired MSA to ensure we can get efficient number of the final decoys. And in the structure modeling stage, we actually taking some ideas from Warner Group. For example, either using the template or not, open the dropout rate or not, or using different pre-trained parameters from AlphaFold2. Later, we will again cluster the structure decoys by MoClass. This pipeline shows the hybrid modeling method used in ensemble fold. In the input stage, we will use DeepMSA2 and RMSA to collect the MSA for protein component and RNA component in the hybrid targets. Additionally, we will use protein long-range model and RNA long-range model to produce the feature embeddings. And the MSA-based features, protein long-range model-based embeddings, and template-based features will be input to the feature blocks and later passed to the structure module to generate the decoys. To ensure we get efficient numbers, so we will using a lot of combination of the MSA that generate from deep MSA2 and RMSAs. Again, at the final step, we will cluster those decoys and select the model from those clusters. Yeah, this is the order pipeline we use in custom system. Okay, we can check some results of our method. This slide summarizes the overall results of our pipeline. Here we list all the protein-related indemnable targets. This figure, we're using the CHEMS score assessment our results, and this figure shows the CHEMS score of the model from indemnable fold. Blue is the first model, and red is the best model from our pipeline. From this figure, based on the best model, we can see almost all of the protein-related targets we can generate the correct fold because the CHEMS score are greater than 0.5. But we still can find the hybrid-related targets. They are much difficult to predict compared with the regular protein targets, as mentioned by Guy. For this case, this is the protein. This is a protein monomer targets that can bind the ligand. And here we align the two states experimental structure together, and the apotype shown by the blue and the holotype shown by red color. We modeling this target as actually without any ligand, so just the protein itself. This figure shows the CHEMS score of the DM fold decoys aligned to the holotype and the apotype. So you can see our decoys actually cluster as 3 clusters by our mode cluster program. And we can see this cluster actually is much close to the apotype. And if we track the this source of those clusters, we can see each cluster actually came from a different MSAs. That means different MSAs perhaps can generate a model in different states in our deep MSA pipeline. And after we feed in those DM fold models to the REMC simulation, we can find a new cluster or decoys size appears here. So if we check the decoys and check their final models, we can see this final model actually is much close to the holotype compared with those models from DM fold. That means the REMC simulation helps create a more diverse set of the models, which perhaps are very helpful for indemnable target modeling. And another thing, as I mentioned, the model from each MSA sometimes corresponding to the different states in indemnable targets. This is another target that Guy already mentioned. Is a DNA protein hybrid targets. It's very interesting targets in this hub. This target has 2 forms, V1 and V2. In V1, we can see the longer DNA arm actually in the same side, and the shorter in the same time, in the same side. But in the vivo form, we can see this right side actually is some twins from each other and form the V2 side, the V2 form. And you can see the protein component in this target also has 2 forms, one bind to the longer arm, one bind to the short arm. We actually modeling these targets as the hybrid targets by our pipeline. And again, when we check the clustering results of our decoys, we find 2 large clusters with the highest confidence score shown by here. And we select the model with the highest confidence score required from each cluster as the final model. And when compared with the experimental structure, we can see this model actually is very close to the experimental structure as the TM score or greater than 0.7. So this case means our structure clustering method actually works well for picking up the correct model for each state, at least in this target. And this target, the modeling method we use in here is almost the same with the last target. So we can skip the slide here. This is a tree more complex with two states. One is called open state, one is called closed state. And we're modeling this target again using PM4 example fold. And after the structure clustering step, we can find 4 cluster occurs. And we rank those clusters by the confidence score of their members. And we show the top 3 clusters. Actually, based on the confidence score, we select the model from cluster 1 and cluster 2. We select the final model from those 2. And if we check the model from cluster 2, you can see this structure has a very extended structure. So we believe this is the open state, and we select the model from cluster 1 as the closed state. However, if we check the experimental structure, definitely the open state should be came from cluster 1, and the closed state should be came from the cluster 3. Which cluster 3 you can see the confidence score is slightly worse than the wrong cluster, cluster 2. So this target shows incorrect QA score ranking prevent us from selecting the correct model. And this is another case with is a dimer complex with 2 different states, but the difference between these 2 states actually quite minor, and which can be which is shown in here. So because the native structure or experimental structure are quite close, so our modeling method can't generate different decoys, which means almost all decoys are identical, and our clustering program failed to distinguish them. So all decoys fall in the same cluster. As final, we can see the final model also didn't capture any difference in this selected region, although their TM score is very high to the native structure. So what we believe currently predicting ensemble structure with minor difference actually is very challenging in our pipeline. Okay, these are some summary. So what we think went right in our ensemble fold. Actually, I believe it's contributed by 3 key points. One is the diverse set of the MSA. Another is the knowledge base potential guided REMC simulation. The third is the structure classing program works very well for picking up the model in each state. But there are still some challenging things in our ensemble fold. For example, the confidence score ranking problem. And another problem is predicting ensemble structure with very minor difference. This is still very difficult. Okay, I would thank all my team members, especially Dr. Gang Hu and PhD student Wen Taoni, who developed the hybrid modeling pipelines. Thank you for your attention. Yeah.